physics experts down here from UVM. This is Luke and Dave, and they are going to be doing all kinds of really cool experiments that, well, they're going to be awesome, that I wouldn't be able to do for you guys on my own. So thank you so much to Dave and Luke for being here. And I'm going to turn it over to them, and you guys are going to be amazed by the stuff that they brought down. So thank you guys.
All right, welcome. So glad you could join us on this day. And I've heard, who's heard of a magnet? You guys have studied these before. So what can you tell me about magnets? Who knows something about magnets? Yeah?
There are 3 different kinds of magnets.
3 different types of magnets. Can you give me one of those types?
Natural.
Natural magnets. Can somebody give me another type of magnet? Temporary magnets. And what's a third type of magnet? Permanent magnet. All right, so we can have things that are sometimes magnets, and things that are naturally magnets, and things that are basically always magnets. All right. What else do we know about magnets?
Like 2 poles, a North Pole and a South Pole.
A North Pole and a South Pole.
And if you go north with the south, or south with the north will stick, and if you go north with the north, or south with the south, they'll south.
So if I have 2 magnets here, what do we expect to happen if I bring them close together? What do you think is going to happen? They're going to stick. They stick. All right. So that red side stuck. And now you say there's opposite sides. So if I flip this green one over, what's going to happen? What do you think is going to happen?
They're going nuts.
So I'll try and push them together, push them together, and whoop. What happened there? I tried to stick the green side to it, and it repelled. Do you ever, who here has a brother or a sister? You ever feel like sometimes you get along with your brother and sister, and sometimes you can't be in the same room? Maybe you just need to turn around. So, this is what we do with magnets. Normally, we can stick them together, we can use them to push apart, but there's lots of other things we can do with magnets, especially if we start getting strong magnets. Now, these are the type that you might play around with on a daily basis. But up at the University of Vermont, in the physics department, we have slightly stronger magnets. And we can do some other things with those new magnets. Now, normally, magnets attract or repel. But if I have a piece of copper, this is a big copper plate, does copper stick to magnets? Who thinks copper sticks to magnets? Who thinks copper and magnets don't stick together? All right. So if I put my magnet on this copper, it doesn't stick. So magnets don't stick to all metal. They only stick to some metal. So we just showed that copper doesn't stick to a magnet. But what if we have a strong magnet? Maybe I just need stronger magnets.
It's not going to stick.
Is it sticking?
Try picking it up off the table.
Try picking it up off the table? So I'm going to pick it up off the table?
No. Pick that blade up off the table. Now turn it this way. Turn it this way. Oh, it doesn't stick. And move your hand.
And move my hand.
Keep it active. It doesn't stick. Copper isn't made out of iron.
Not made out of iron. All right.
The only metal it can stick to is iron.
Ah.
Not
But now watch.
and some other magnets. Yeah.
It looked a little funny. Let's try that again. I'm going to drop this magnet. Is everybody watching? What's going on there? What? Can I drop it a little higher? So if I can get it to fall flat, what happens? Or if it's on an edge, it slides, but does it slide fast or slow? Slow. So I've got a related thing here. I have a bunch of magnets, and this time, instead of dropping the magnet, I'm going to drop copper. Now, does copper stick to magnets?
No.
No. So this copper should just fall, because it's big enough to go down that pipe, right? So it should just fall. You ready?
It's slow.
I thought you told me copper didn't stick to magnets.
Yeah, because it didn't. It still moved out of the way. But
It did still move out of the way.
It attracts a little bit, so it's going down slowly. Right.
Going down slowly. All right. I have a question for you. What do you see in this ring that's different than this ring? Kind of yellow. And what's right there? There's a line, there's a hole in this ring. Can you see that hole? So we've got one ring that has a hole in it, one ring that doesn't have a hole in it. So now, I used to do this with my wedding rings, but my wife got upset. This one has a crack. It's a great description of it. So we've got a crack in the ring. So, if I've got a ring made of copper that's solid, it falls really, really slowly as it goes past that magnet. Do the one with the crack. Who wants me to do the one with the cracking? All right, let's give that a shot. There's our crack. It goes faster. Who saw it go faster? So, how often do things with cracks in them go faster? So I'll release them at the same time.
1, 2, 3, go! That one went faster and that one's going slow. Faster.
That one went faster, that one went slower. All right. So dropping a magnet near copper, or dropping copper near a magnet, maybe it's something special about copper. I have an aluminum plate.
Aluminum doesn't stick to magnets.
Aluminum doesn't stick to magnets? Let's
No,
test.
it
It's
doesn't.
always a good idea to test in science.
We had a whole discussion about this. Yeah, we had a whole discussion.
But I think this might be a magnet. Who thinks this is a magnet? My
Because
magnet
that's
certainly stuck to
sticking
it. Yeah.
It's either an iron thing or a magnet.
Alright. Well, let's check what happens if I drop this magnet through aluminum now. So now we're testing different materials. Are you ready? It's not coming out. It's stuck inside. The pipe isn't big enough.
Oh, we're done.
Can we try that again? Can everyone see? Drop that in there. Now, this is the same size, and so maybe it's just that it's a tight fit, and you're trying to squeeze through something that's tight and it takes a long time. So if I try this one, how long do you think it's going to take? Is it going to take 30 seconds?
The same amount of time.
The same amount of time, so it's slowly going through. Are you ready? Ready? Set?
Oh, faster.
Same size. So is it the size that matters?
No.
Oh.
It's the weight.
The weight. Oh. So one of these is heavier than the other. Everybody ready for this?
Yes.
All right. So Dave is going to stand right there, right in the middle, and I'm going to stand behind him. That's why Dave and I work together, because we're different heights. Dave's going to hold his hands
We're
out,
twins.
and I'm going to drop these at the same time. Can you catch both of them?
I'm going to try.
All right. So if it was the heavier one falling faster, then Dave should be able to catch this one first and then this one, right? 1, 2, I'm going to release on 3. 1, 2, 3. Did they fall at the same rate? Oh, so it wasn't the heavy one. Let's have a hand for Dave, my beautiful assistant.
I can say that the one that fell slower is heavier than the one that fell faster.
So
By quite a lot.
he says the heavier one fell slower. So you thought that, which one of these feels heavy? Put both hands out. Which one feels heavy? This one. So she says this is the heavy one. And now let's test that even more. This is the heavy one. -1. All right. So, who's ever had a bright idea? All right, some of you have had a bright idea. And now, if I have a bright idea, how do we symbolize that somebody has a bright idea? What do we show? How do we show somebody having a bright idea? With a light bulb? A light? All right. So I have a light bulb, and I have a big red button. You can tell I'm a scientist because I've got a big red button. So now, if we press the big red button, what happens? What do you notice when I press that big red button? It turns on the light bulb. Do we see any batteries in my light bulb? No. Do I see a power cord going to the wall? From this. So we get electricity from here. So I'm going to hold it so that it's not touching the wire.
Take it off that thing and press the button. See, I told you.
So when it's near there, I can make it light up even when it's not touching.
But there's also this black.
There's this black stuff in the center. That helps. And you guys know that iron sticks to magnets. So that's a bunch of iron. If I take that stuff out, all right, we're scientists, we like to investigate. Only a little bit. So now if we put the iron in, much brighter. Oh. So we know that iron helps magnets, and we know that the iron helps me light up the light bulb. So what do we think might be happening here? Could I be doing something with magnetism?
Yes.
Am I doing something with electricity?
Magnetic electricity. Something like that.
Something like that. Electromagnets?
Yes.
Who's heard of an electromagnet? Oh. Alright, so we have an electromagnet here that I can use to turn on a light bulb. Now, is there any light bulb on this?
No.
And does aluminum stick to magnets?
No.
So do we expect anything to happen if I put there and press the big red button?
Try it.
It might conduct electricity. When something conducts electricity, it gets warmer.
Yeah.
So that aluminum ring might get hot.
Yeah, try it.
Is that what we expect? That it's going to get hot? What do you think? Oh, you're not raising your hand. All right.
Or maybe it's a,
Can I get you to come up here? No? You want to come? All right. Can I get you to press this button for me? How did you press the button? We expected it to get hot. What did it do? It went flying off into the air.
Do it again.
Try that again. Who expected that to go fly? Great, you should all go to the UVM physics department. We would love to have you take some of our courses. We explore this kind of stuff. So this goes flying. Now, we had we said sometimes magnets attract and sometimes magnets repel. So if this goes flying in the air, is it attracted or repelled from my black ring? Attracted or repelled? Repelled. It's flung away. So I must have turned this into a magnet? A temporary magnet? Oh, that was one of our types of magnets that we talked about earlier. So I can create an electric current that creates a magnet that creates another magnet. We can induce magnetism, even in things that are normally not something we associate with magnets, like aluminum. Now, magnetism is even weirder than that. If that wasn't odd enough, we've talked about sometimes magnets attract, sometimes magnets repel. But I've got a little bit of my lunch here on a string. Who likes grapes? And do grapes stick to magnets? No. But what if I bring a really strong magnet near a grape? Do we expect anything to happen? No? Maybe? I'm going to do it, so I hope something happens. Did I touch the grape? So we know that that part's iron. Alright, so it's moving this way. I'm going to bring my magnet in, and without touching it, without slamming my hand, use the iron. Both of these are important parts of the steel. What's happening to the grape? Did I touch it?
No.
So maybe the grape is just a magnet. So if I touch the other side, it should get attracted to it, right? So we had that side, I can repel my magnet. I can repel the grape with a magnet without touching it. And then I'll come in on the other side, and if that was just a magnet, then I'd expect it to be attracted, but instead, I can push my grape around. Now, science is useful for a little more than pushing grapes. We do lots of things with magnets. This jumping ring demonstration, this is an example of a transformer, something that the power companies would use to send electricity to your house. An understanding of electricity and magnets allows us to do different things that we like to do in our lives, like have light, play video games, all these great things. All right? And scientists are constantly working to develop new things. For instance, look, the grape trick is an example of diamagnetism. Most things are either unaffected by magnets or attracted to magnets, but some things are actually repelled by magnets. So we have two examples of that. We're going to set one of them up right now, and then while it's getting ready, we'll do the other one. So who likes to take notes in school? And who likes to come to a science museum where you don't have to take notes? So we took the pencil lead, the graphite, out of a mechanical pencil, and we put that in here. And we're going to pause for a moment and add some liquid nitrogen to this other thing. So you can see the liquid nitrogen come on.
Put a magnet on top of those two black items.
How can you see what's
All right. So that's going to cool. We've got something really cold, liquid nitrogen there to cool that off. And then while we're doing that, I have another example of diamagnetism. And you, at the very end, you can come up and see this one. But I've got a bunch of magnets here, and I've got a little bit of pencil lead from a mechanical pencil. And if you see it, it might be easier to see here, or if you can see it up on the big screen. If we turn off these lights.
Yeah, that might work against it.
Might.
You want to find out?
Yeah. So we've got a little, and it's actually floating in that channel of magnets. Just jumped out. So, diamagnetism is something that happens at the molecular level. All right, now am I big or am I small? Big. And are you big or are you small? All right, but how big is a molecule? This small? Smaller? This small?
I can do it.
So take your fingers and put them how big you think a molecule is. You got your fingers right next to each other? That's how big a molecule is. We can't see it, but some of these interactions happen at a molecular level. At a molecular level, water molecules end up repelled from magnets. But we can also have other things that are repelled from magnets, superconductors. And this is something that scientists have been working on for several years and we keep getting better at. And so we have a superconductor that works at low temperatures, colder even than Lake Champlain today. So that's why we have to have liquid nitrogen. And once it's a superconductor, the magnet can make electricity, the electricity can make a magnet, and it actually ends up levitating above that magnet. All right? So all of these interplays, you don't have to understand everything that's happening right now, but know that there's lots of fun things for you to grow up and investigate, or to find jobs in, or to invent the next big thing. So thank you very much for coming out and spending a little bit of your day with us. Thank you. Physics students are out in the main gallery and they will happily answer questions and have more activities and demonstrations. And if you'd like to come up, you can see some of these nearby. Stay with Girl Scouts, stay with your troop leaders.
For anybody who came in late, we're going to be doing this again at 1 o'clock, so feel free to come back and join us to see the whole program if you missed any part of it.